starting from the fact that my computer just didn't boot up. So I have to use a different computer, and something is happening to the system. It's to the system. It's not on the computer. Well, it's not a question for you to answer because we know the answer. That's the same experiment. I just want to show it one more time. What we have here is two bulbs connected. Actually, first, the connection is supposed to be in parallel. So I gotta put the jumper back, and so parallel. And whichever is brighter is supposed to be a 100-watt bulb, whichever is dimmer is supposed to be 40, so bright, dim, natural, because in parallel all devices consume the power according to what we read. Every device has a reading, power, power, power. That is assumed that they connected to 120-volt power outlet. For the bulb, the power also assumes that it's been running for some time, so the temperature reaches the operating temperature, because the resistance in general depends on temperature. It rises with temperature. So now we can connect these two in series, and now we know the 41 is brighter than the 100. So we know that, and we started talking about why, and well, this is what we did, and right here we just need to add very simple algebraical, not physical notion. If you look at these two, well, let's divide it. Yeah. Parallel wiring. If you look at these two fractions, P1, P2, if R1 is, well, let's say less than R2, because R1 is a denominator and the voltage is the same for both, that means P1 should be greater than P2. But for series wiring, connection in series, now the same bulbs share this, the same current. So now if R1 is less than R2, the algebra tells us that P1 should be less than P2. And we know very well brightness is just an expression of a power. It dissipates. So less power, dimmer, more power, brighter. And of course, if we talk about two specific bulbs, 100-watt bulb, 40-watt bulb, everything now is goes to a question about the resistance. Wrong keyboard today. So this is the question I want to ask you. What do you think about the resistance? Assuming, of course, both bulbs are hot, they reach operating temperature, and the information we've discussed should help you to answer this question. And while waiting, I want to, yes? What do you think? What do you think about what might happen to the resistance of a bulb if we screw it in a socket or unscrew it, does it affect the resistance? Well, we have a conversation, we have to answer. Does it affect the resistance if the bulb is in a socket or just lies down? How? We don't care about temperature, technically. It's just a mentioning of the fact that, in general, we should take into the account. We assume that the bulbs are hot enough, wherever. It's the same bulb. It's hot. Some other bulbs might be connected to it, but still, how would it affect the resistance, which is the internal property of the bulb? How? What do you think? The internal property of the bulb, the resistance, depends on the length of the filament, the diameter of the material, of the size of the atoms it's made of. So if the bulb is connected to other bulbs, or maybe not connected to other bulbs, does it affect its resistance?
I was not sure about this, but I know that the less bright one would have more resistance. The 40-watt one.
This is a resistance box. Well, I wish I could break it and show what's inside, but basically just a bunch of coils, similar to the coils we've used to measure the resistance. So the resistance R depends on if it's a wire, area, length, and material. These three variables define resistance: area of a wire, length, and the material. So let's say I connect it to a battery. This action, does it change the length of the wires inside this box? Does it change the diameter, area of a wire? Does it change the material it's made of? All right. Instead of a battery, I connect it to a second box. This action, does it change the length of this wire in this box? Does it change the diameter of the wire in this box? Does it change the material it's made of? So, does it change this action? Does it change its resistance? No. There is no reason. In physics, change happens for a reason. It's in life everything without reason. But in physics, if you want to change the resistance, you have to cut a wire or add a different piece of it. So if you do not change area, length, and material, assuming temperature also is constant, you do not change the resistance. And everything we said about this box can be applied to any device, to any resistor. It's an internal property. Why do you think the bulb By the way, have you ever read the bulb writings? What does it say? It says two numbers. It says voltage 120 volts and power 100 watt. That's it, nothing else. So it doesn't say 120 volts, 100 watt, only when it is connected to a different bulb. No, it doesn't. It is assumed that if you plug it in 100 volt socket, it will give you 100 watt power, which means 100 joules per second. And it doesn't tell you that you cannot add any, you cannot plug in any other devices in your room. No, it doesn't say that because it doesn't care, because it's internal property of the bulb. So you can calculate the resistance of this bulb, and it will remain no matter what until you break it. Same as EMF is the internal property of the battery. If it's a fresh, new battery, it will give you 6 volts no matter what. No matter what. You can connect 2 bulbs, 3 bulbs, 10 bulbs in any circuit you want. Still, this battery will provide exactly the same voltage, which, yes, 6 volts for this battery. We just read it. So the rule is simple. An internal property of an object doesn't depend on the external circumstances. It's put into. So in this situation, again, this disclaimer, not important. It's just something we know in general about resistance. Well, by the way, why? Why does it change? What do you think? We heat it up, take a wire, heat it up. The resistance generally increases, rises. Yeah. That's a good thinking. But the coefficient of linear expansion is very, very small. If you remember, it's 10 to the negative 6th usually. So that couldn't affect much of the resistance. That will affect, but not as much as it actually happens. There's a second reason for that, which is atoms, bless you, atoms start moving faster. So they just kind of cover more area to prevent electrons to get through. That's it. And when we cool it down, atoms move slower and slower. And some materials eventually can become superconductive, no resistance at all.
Actually, zero resistance.
Yeah. Yep. Technically, those materials ideal magnets, but magnetism and electric current related, and we will talk about it later. So in those materials hate magnetic field. They don't allow magnetic field penetrate inside, and to do that they have to generate electric current which can last forever. Just Google superconductivity. Well, the answer, of course, is in the bulb. So again, if we read it, it says, let's say 100 watt. What's 120 volts? So there's a filament right here, and power is related to voltage and resistance. So 100 watt should be equal to 120 volts squared. This is actually what we used to call yesterday root mean square value, because in the real socket it constantly changes. So that will be the resistance of a 100 watt bulb, and we can solve it. $12 squared. That's it. And we can calculate just straightforwardly the resistance for a 40-watt bulb. That's just a number. Same 120 volt voltage divided by 40 ohms, 40 watts. That's the resistance. That's it. So it turns out it has more resistance. So if we go to our previous slide, less resistance, more power, but only when they connect it like they're supposed to be connected, in parallel. In series, the one which has less resistance will be dimmer, less power. Any questions? All right, moving on. So that's why I need these two boxes. And the switch, if I have it, well, I don't really have it. By the way, while I'm preparing the demonstration and while you're thinking about this question, I want to mention that take a mental snapshot every time you see a new slide, just in case we lose it again. Something is happening here. The zone. Here. So what I wanted to say is that evidently I've learned like half an hour ago, some of the students do not read the lab manual, at least in full, and so do some teaching fellows. Because I was asked about what to do about diode in a lab, and I can tell you, because I wrote the manual, I know there is a sentence which says, if you give in a diode, don't use it. So if you try to use it, and if your teaching fellow try to help you, that's it. You didn't read the manual, and he didn't read the manual. So first what we do is, battery, we need a battery. So we just need a battery and we need to connect. By the way, you know that means a positive terminal, has nothing to do to Red Cross. So we gotta put it in, so we want to measure current. Now we need to complete the circuit. Now we need to connect this to, what is it? 100 ohms to connect to, well, about 50 milliamps, 6 volts, 100 ohms. And what we are trying to do is we're trying to connect, let's do it like this, a second resistor. How do we call that?
Are those arrows signifying the direction?
Increase or decrease, of course. The current might not change. The current reading might increase, or the current reading might decrease. All right. So where's your answering device? Did you enter your answer?
Yeah.
What did you say?
I think it's number 2, but I think that's
Number 2, okay.
it should be number 3.
So you want to change your answer?
I already
What should happen to the total resistance? That's basically the question is about. If you're adding an additional resistor, does it always mean the resistance goes up? This is your initial circuit, actually. I always advise draw the actual circuit. This is current number 1, let's say. And now what you're doing, adding a resistor. The question is how, and in this situation, how do we call it? Parallel. So now R, and here we have R and another R. The same EMF, the same EMF. This is current number 2, and the question is, what is the relationship? That's it. And current 1 will be equal to EMF over R, and current 2 will be equal to EMF over R equivalent. So now the question is about R and R equivalent. Which is higher, which is lower, or the same. So we need to write something for the equivalent resistance. What should I write? If I have two, in this actual example, identical, yes, 100 and another 100, R. So the equivalent resistance will be equal to the mistake you're making is thinking. You should be writing. Did you write the expression for the equivalent resistance? Did you? Can I see it? So write it. You have to act. You can't just wait. You have to act. The equation for the equivalent resistance for resistors connected in parallel is, so write it. 1 over R equivalent equals 1 over R plus 1 over R. Now we have to do a different action. We call it application. We have to apply. So we have to solve this equation, solve it, and see what it tells us. So if you solve this equation, R equivalent will be equal to, what do you say? R over 2. This is 1 plus 1 is 2, common denominator. Then we flip it. In fact, if you have, that's a handy thing to remember. If you have many identical resistors, identical, that's it, etc., etc. Let's say you have n identical resistors connected in parallel. R equivalent will be R divided by n. We given more room to electrons to travel through. More extra room to get through means resistance must decrease, must go down. And if all R are the same, so evenly split. Now, so we can answer, we can erase this question mark. R is greater than R over 2, right? And now we can erase this question mark. So current will increase, yeah. The current will increase. Opposite of that. We use smaller denominator, the current will increase. Actually should be doubled in this situation. So what do I have to do? I have to I have to finish my connection. That's it. Take it out, put it back. Of course, it's never exactly twice or 3 times because battery has internal resistance, wires have internal resistance. Even this device has some resistance, but it's very close actually. Any questions? This again, a very common strategy we can use every time we need to answer a question about what might be happening to electric current or voltage, resistance, power. So electric current, okay, increases. And this is not a question, but let's think about it. What would you answer now? We again can play with things. We just need a battery, wires. I'm not hiding, I'll be back. And a bulb. Now, I'm going to add a second bulb in parallel or in series? In series. And if I add an additional element, an additional resistor in series, how does it affect the total resistance? Increase, yeah. Now electrons should travel through more resisting elements, and if we increase the total resistance of a system, electric current should decrease, and if we decrease electric current, now they should be dimmer, right? So, and of course, if we look at algebra is very simple. Here, electric current is EMF over R, but here electric current will be EMF over R and R. And means add. Now, what do you think should happen here? Again, we start from one bulb, and now we want to connect a second bulb in parallel. So all I have to do is just plug it in. And what do you think should happen to the brightness of this bulb? Well, this is dim, and it will not be dim anymore, so right, brightness goes up. What about this one? What do you think? All right. Why?
Because power is U squared over R and
The voltage is the same. And if I add an extra bulb, it doesn't change the voltage applied to this. It's still the same voltage, and this is the same voltage, so it doesn't affect the brightness of this bulb. And this bulb should be bright as this one. Yeah. Same thing. That only works when you have a very fresh battery. If the battery is way below what it's supposed to, in that case, you know, it might not. This might be slightly affected due to internal resistance, but in general, you see, almost, yeah. Every time when we make a change, we just have to ask a question: how does it affect total resistance, and see what's happening. So here, what should we write? Current number 1 should be equal to, well, 14 divided by R. It's a good thing today is not Wednesday, but still, let's make it better. And current number 2 should be equal to 14 divided by R over 2. just like in experiment with 2 boxes. And all right, what do you think should happen now? And this is a question you should answer on a web assignment. This is what I'm going to do. I'm going to connect. You didn't see it. Forget it. Erase it from your memory. Answer question. Well, okay. When the switch is open, we only have one element. We don't really need anything else. And when the switch is closed, we have 2 elements connected in parallel. This is R, this is R. What is the resistance of a wire? So what's going to happen to the electrons? Let's say, imagine you are an electron and you have a choice to make. It's very hard to go through that door, but through this door, very easy. You're a normal electron, so of course you go through the easy way. So of course all electrons now will travel through this wire, which means no electrons will travel through the bulb anymore. That's it. And of course we can calculate the equivalent resistance using equation for resistance in parallel. You would have to just divide over 0. 1 divided by 0. What does it give you? So R equivalent will be equal to 1 over R plus 1 over 0. That's the calculation. And that's all I want to say about it. All right. So in all situations like that with a switch, we should imagine what will be happening to electrons. And we know what's happening here. We close, all electrons run away. If you had 2 bulbs equally bright, if you close this switch, now all electrons after this bulb will travel through this closed switch, which has no resistance. So this will go up, dark like that one. And here, if you close the switch, all electrons, well, electrons travel from a minus. All electrons will travel like this. These bulbs will be outside of the circuit. Now, of course, we can calculate things in this situation. Whatever circuit we have to redraw it. We cannot use the circuit, give it to us, never. We have to draw a circuit using our own hands in a way we like, and this is how I like it. Bulb number 1, bulb number 2, and the battery is here, 20 volts. Identical bulbs. How do I know? I can read. Identical. So we just saw a circuit like that. Identical bulbs, the same battery, equally bright. What about voltage across each bulb? Well, delta V1, delta V2. Same bulb, same resistance. Where else do they have the same current? That's very important to make a statement. Where else do they have the same? Electric current is the same. So electric current on one hand should be equal to delta V1 over R for the first bulb. On another hand, delta V2 2 over R. Since the resistance is the same, the voltage should be the same. But together, first voltage plus second voltage should give EMF. So, can you tell me what two numbers, if we add together, equal to 20, but also would be equal to each other? How do you know? Can you prove it? Yes, you can. By writing 10 is indeed equal to 10, and 10 plus 10 is indeed equal to 20. This is what in mathematics called try and check. But of course, we also could solve it as a system. This is a system like x equals y and x plus y equals 20. How do we solve it? I don't know, but you do. All right. Now we should think about what should happen to the brightness if we close the switch. Well, let's just see it. It's, again, not a web assigned question. Let's see. This is what one of the best features of physics. You can play with toys. You, of course, need these toys. Where do you buy them? Where can you buy? Where can you buy the battery? Home Depot. They should pay me for commercials. All right. We start from two bulbs connected in series, and now the third bulb will be connected in parallel to one of these bulbs. And in parallel means just take two wires. So, you know what? Let's try to capture it on a camera and hope it will not break the system. Not sure. Well, that's the best probably we can get from this. Now, what's your expectation? And compare. Well, first of all, if I connect a second resistor in parallel to the first, that should change the resistance of this part of a circuit. How? We know parallel means lower. So right now I have R, and after that I will have R and a half of R. So total resistance actually should decrease, which means total current should increase, which means a total current travels from the battery and goes through this bulb. If it increases, this should go brighter, but these two should go dimmer, because that current after that splits. So that's the idea, see? Dim, brighter, brighter, brighter. But this current, even if it's higher than before, evenly splits. So each current traveling through each bulb here is lower than it was before. But of course, we just have to do it mathematically. If you don't believe, you look like you don't believe. You don't believe what you see? I don't do magic. I wish. All we need to do is just calculate the new voltage across each bulb. That's it. And if voltage changes, it becomes higher, it means more power, brighter. If voltage drops relative to previous case, it means the bulb should be dimmer, and of course, yes, I can, and I should, and I will, and I am, and I did. Thank you for reminding me. This is how I like. I don't like battery on the left or on the right. I don't know why. I just don't like it. So first, so this is, I'm sorry. It was 120, it wasn't 20. Shoot, now I have to correct everything. 120, 120, so 120. So that's supposed to be now 60 and 60. All right, now we are all on the same page, because all we did, we just closed the switch, so we should keep the same battery. 120. Now, of course, the first step is to simplify the circuit. That is always the first step. To redraw the circuit after we have replaced some elements with the equivalent one. And now we can start talking about voltage. Delta V1, delta V2. Question, do you think now the voltage is the same? No. Now it cannot be the same, because even if the current is the same, the current traveling through first and second part of the second circuit, but the resistance is different. This is R, right? Still the same bulb. But this resistance is equal to what? What should I write? What should I write? What should I write for this? Now I want someone from that group. Anyone from that group. You can communicate, you can talk, and then say, what should I write? Just say anything. Whatever you say, I will write it. All right. No. That should be what you say. R over 2, that's exactly what we should write. For equivalent resistance of these two identical resistors. And now we can set up the same ratio as before, since the current should be the same. That on one hand should be equal to first voltage divided by the resistance of the first element. On another hand, it should be equal to the second voltage divided by the resistance of the second element. So what does it give us? It gives us a ratio. Delta V1 should be twice of delta V2, which is actually makes sense. Twice more resistance drops the voltage twice, well, lower, we can say, if it drops. But, of course, if we add those two together, we should get 120. So, first voltage plus second voltage should be equal to 120. So the question now is, what two numbers, if we add together, give 120, but one of those numbers is twice larger than another one? Yes. How do you know? How can you prove it? So 80 is indeed equal to 2 times 40, and 80 plus 40 is indeed equal to 120. So that's a proof, a solid proof. On the other hand, you could do some math. X equals 2 times y, and x plus y equals 120. That's a system. How do you solve it? I don't know. You do. So that answers the question about the voltage across this bulb, 80. A voltage across the top bulb, 40 volts, and the voltage across the bottom bulb is 40 volts. But before, the voltage we had for these two bulbs was 60 and 60. So for bulb A, voltage goes from 60 to 80. But for the bulbs B and C, well, for the bulb B, the voltage goes from 60 to 40. And since they have the same resistance, when voltage goes up, power goes up, brightness goes up. When voltage goes down, power goes down, brightness goes down. Any questions, please? Yes?
You said there was a scenario when the current goes up, the voltage is
It could have been if we didn't have bulb A, when everything is connected directly to the battery. Again, case A. We are adding a second resistor in parallel to the first one. It doesn't affect the first bulb at all. Case 2. You already have something in between, and then you are adding a third one. In that case, everything changes. How? Well, we know how. This is how. And these are potentials. So we talk about voltage, but of course, where's my? We can trace the potential. We just have to set one point to 0. It makes things easier. And of course, we always set to 0 potential, the negative electrode of the battery. So 0, 0, 0, 0, 0, 0. And now here from 0 to 60. So this potential is 60, and here from 60 to 120. 0, 0, 0, 0, 0, 0, 0, 0. Now here from 0 to 40, this potential is 40. Now from 40 to 120. 40 is initial potential. Well, we can not initial, current travels like this, but 40 is the potential on the right electrode of this bulb. 120 is the potential on the left electrode of that bulb. What is the voltage across 120 minus 40? 60. That's what is. That's what voltage is difference. All right. Please, this is a very important question, so I will even look at your answers. So. Wrong button, wrong button. That's the question. Back to the question. Oops. So this is a circuit. Well, it has 5 different elements or devices. Battery number 1, battery number 2, bulb number 1, bulb number 2, and the switch. And the switch is open. We marked 2 points. We could do more, but there's A, there's B, and the question is, can potential at point B be set or cannot be set to 0? And survey says okay, one more time. Question 5. Electric potential at point B, finish the sentence, cannot be set to 0, can be set to 0, and other. Pick wisely. So we've had different type of questions before. Like sometimes a question requires some thinking. This question doesn't require any thinking. This question is about pure knowledge. Electric potential is to be measured relative to a reference point. Reference point is always up to us. We can choose any point and we can make it any potential, and then we can calculate or measure all other electric potentials relative to that. That's it. Because Ohm's law, the most important law we use, the Ohm's law, says voltage is related to electric current and resistance. Voltage, not potential. And if we choose the reference point, it doesn't affect the voltage. It doesn't affect the difference. So yes, it can be set to 0, because any point can be set to 0 or to anything else. I can set this point to have potential equals negative square root of pi. That wouldn't be wise, but I can. And choosing point B also is not actually wise, because it's connected to a high potential electrode of the battery. And the most convenient, the most convenient choice is setting point A to 0 potential. So 3612. Keep forgetting plus minus. Yeah. All right. 12 volts and 8 and 6. 8 ohms, 6 ohms. So this point is connected to the low potential electrode of the battery, actually both, which makes this point to be most convenient to be grounded, so it doesn't go anywhere forever. So this potential, VA, I want to set to 0. And relative to this potential now, we can trace potential easily. Yeah. What does battery do? The battery increases potential from 0 to the value we read. So this potential should be equal to 36 volts. 0, 0, 0, 0, 0, 0, 0. Actually 0, 0, 0. So here, this electric potential is 0 volts. So this electric potential is supposed to be 12 volts higher. 12, 12, 12, 12, 12, 12, 36, 36, 36, 36. Now you can tell me what's supposed to be voltage across this bulb be equal to? What's supposed to voltage across this bulb be equal to? What's supposed to be voltage across this bulb equal to? I have no idea. No, I don't know where B should stay in this sentence, before or after. I know the voltage, 36 minus 12, 24 volts. Now what is happening inside that bulb, the second one? Nothing. When the switch is open, there is no current. If there is no current, the bulb actually doesn't change the potential. So up to here, the potential still will be equal to 0. And you can see again why, despite the fact that every other textbook uses letter V for voltage and same letter V for potential and same letter V for volts, I don't do that. This is potential, electric potential, and this is voltage, my voltage, Valentin Voroshilov voltage. Because I don't want to confuse myself. So if you don't want to confuse yourself, you should do the same. So the voltage across the open switch right here, what is it? It should be equal to difference between 12 and 0. Delta V here is 12 volts. That's it. That's how it works. Any questions? I got more examples. So if you don't have questions, you want to close the switch? She wants to close the switch. All right. Thank you. But now you will have to tell me everything. Where do you want to choose the reference point? Same. I would do exactly the same. Why would change it? It worked well for us. So let's ground it. So what does that change? Only one thing. Now there's supposed to be a current traveling through the second bulb. Potentials don't change. So still electric potential here is 0. Electric potential here is 36. And electric potential here is 12. And this voltage still is equal to 24 volts. But now, due to electric current, well, now actually we should name the currents. Here we called it just I. And this current I should be equal to voltage 12 over resistance 8. 12 over 8, or 3 over 2, 1.5, 4 and 4 amps. Okay. Now we should call this current like 1. And now we have a junction right here. So it probably, well, let's call it 2 and 3. First of all, even if we don't need it, still we can write that I1 should be equal to I2 plus I3 because of the junction rule, law of conservation of charge. Where else should we say? Now, I1 supposed to be equal to what? To, why is it 12? See? And you didn't correct me. I was solving your problem. That's 24. 12 was potential. 24 is the voltage across that bulb. Trust but verify. Well, that used to be my previous rule. My new rule is don't trust anybody.
Any current actually flow towards the positive terminal?
Let's finish our calculation. So the voltage is still 24. The battery was 36 and 12. Yes, 36 minus 12, 24. The resistance of this battery is still 8, so the current through that bulb is still 3 amps. Now, this voltage, delta V2, will be equal to 12 minus 0, 12 volts. So now I can calculate I2, and I2 will be equal to 12 over 6, 2 amps. Well, I3 is supposed to be equal to 3 minus 2, 1 amp. That's it. So now we finish the calculation.
Why would current flow towards the positive terminal of the battery, right?
Because the second battery is much stronger. I mean, the first battery on the left is much stronger. So it overpowers, literally, that battery. Every battery generates electric field, which acts on electrons and makes them move. But that battery on the left has a high voltage, so it generates a strong electric field. And the electric field due to second battery is not as strong. But what is acting on electrons? Always the total net electric field, which is first plus second, and it still will be clockwise in the circuit. Still. You can replace this battery with a more powerful battery, and that will change the current. That's it. If you had two identical batteries, the first bulb would not be on at all because you would have 0 voltage across it. All right, question. So we're adding more and more elements. Now we have 4 resistors. And the question is about first and third. The prospect of solving this problem correctly solely depends on the answer to this question. It's about how do we recognize the wiring. And if you look at these 3 resistors, you can clearly see how they connected, right? In parallel. That's for sure. But what about this and that? What do you say? Hmm? No. If you had connection in series, you would never have a junction. This is a junction. The junction makes it not in series, and if it's not in series, and definitely not in parallel, so the answer is neither. There cannot be junction for resistors connected in series. And I am serious. And since my pronunciation doesn't differ these words, you never know what I say. So, but what we know is those are in parallel. So if we know for sure some device is connected in some way, we just have to simplify that part immediately. It doesn't require thinking, it requires acting. These three resistors must be replaced by a single new resistor. So I don't touch R1, still 3 ohms. But these three are supposed to be replaced with a new one. Please, anyone, tell me what's supposed to be R2, 3, 4 equivalent be equal to. What do you say? 5, yeah. That's a situation when we actually should use time-saving approach. If we have 3 identical resistors connected in parallel, the equivalent is just 1/3 of individual. So 15 over 3, 5. Well, still not the most simple circuit. We can simplify it one more time. Now there is no junction anymore. Now these 2 resistors, one is actual, second is equivalent, connected in series. And now we can replace them with the new one, which should have 8 ohms. And now we can apply the Ohm's law directly, 24 volts over 8 ohms. That should give us electric current of 3 amps. Where? Well, we have found the current here. Clearly, if we go back, one step back, this current will be traveling here, that same I. But if we go one more step back, this current will be traveling only here, up to here from here, I. But here, this current will split. It must. But because those resistors are equal, this current will split evenly between all 3. So this will be 3 amp. Well, this 3 amp. This will be 1 amp, 1 amp, 1 amp. What else can we calculate? Well, it says calculate the power. Well, the power of the battery. We can do it right now because we know the current traveling through the battery, and we know the EMF of the battery. 24 times 3, 72. And I'm going to move on because now it's very easy to do. If you apply the Ohm's law, for each element, you can calculate the voltage across each element. Just multiply 2 numbers, current, resistance, current, resistance, current, resistance. And you can always apply this equation to calculate the power current times voltage, current times voltage, current times voltage. Please answer this question. You see, today you're answering a recording number of questions. I think I may have one more. What do you say? This current traveling through the first resistor is equal to 5 amps. How do I know? I have eyes. The question is about current traveling through the top resistor. Now, everybody who will give the wrong answer, I'm not going to finish this sentence. Pick your answer. Remember, enter. Number 7, right? Who answered 8? You know I can find out. All I need is time. So, if it doesn't change, you choose answer number 1. If this current is higher than this current, you choose answer number 2. If this current is supposed to be lower than this current, you should answer number 3. And everybody has to say something because 14 is not enough. $53 is better. What is the name for this point? So if you don't know the answer to this question, you should write it down and memorize it. That's how it works. What is happening at the junction? Right now, this current should split. How? It doesn't matter for this question. If it splits, that means a part of 5 amps goes away. So if we call them I2 and I3, I2 is supposed to be 5 minus I3, wherever it is. So I2 must be less than 5. And of course, we can calculate. Here, what I see is these two resistors share the same voltage. That's always what we should look for. What some elements might share. And this is what I want to do. This voltage, let's call it 2 or 3, doesn't matter. On one hand, it should be equal to current number 2 times the resistance of the resistor number 2. And also, it should be equal to current number 3 times the resistance. So I3 should be equal to 2/3 of I2, which is natural because if electrons need to make a choice, of course, more electrons travel through the path which has less resistance. They're smart. They're not stupid. So that's why this current should be higher than that current. But also we have a relationship which tells us that if we add 2 currents, we should get a number equal to what? So now, what 2 numbers? On one hand, if we add them up, equal to 5. On the other hand, relate it like this. Which is which? Why it's not the other way around? Because I2 should be higher, 3 and 2. This is a guess. How do we check? 2 plus 3. Is it 5? Yes, it is. 3 times 2. Is it 2 times 3? Yes, it is. What else could we do? Y equals 2 over 3 times x, and x plus y equals 5. How do we call it a system? How do we solve it? I don't know, but you do. There's another way to solve this problem, of course. These two are in parallel. You can simplify it and then just do what we've done before many, many times. But I find this approach kind of more beautiful. Well, first of all, we can calculate this voltage immediately. This voltage will be equal to what? 2 times 3, 6 volts. And this voltage is supposed to be equal to this voltage, supposed to be 16 minus 6, which gives 10 volts. And now, since we know a voltage and current, we can calculate the resistance of that element. So R supposed to be equal to delta V over I delta V 10. I is 5, 2 ohms, right? Okay. Questions, please. That's the last question I want to ask you. What a weird circuit. Most probably drawn by a weird person. Well, anyway, the question is on the board. In this circuit, can we calculate the voltage at the point P? Where is the point P? Here. That's the point P. That's the answer. Please enter the answer. This question, again, has nothing to do to any equations or calculations. It doesn't require any thinking. It requires the knowledge of terminology. A difference between electric potential and voltage. Potential is at a point. Voltage is always between or across. A difference. So this sentence just wrong. It's like saying, I don't know, hot ice cream. So, but we can calculate potential if we set a reference point. And that's what we want to do right now, very quickly, because we are running out of time. When the circuit has only one battery, I always choose the negative electrode of the battery to be grounded. I set it to 0 potential, 0. So this electric potential will be 10 volts. Well, again, this is a very weirdly drawn circuit, first we need to redraw it, make it normal. This is abnormal. So a battery, a resistor, another resistor, just a straight wire. Now straight wire, another resistor, another resistor, and another resistor. We know that they have different resistance. So this we call R, this we call R. That's supposed to be doubled, 2R, 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 R, 10 volts. So what do I see? I see I can simplify the circuit to what? So these two should go together in one, just R. Next step, I can simplify this circuit. To R. These two will be together, to R. What do we see now? I can simplify this. So what do I have now? Battery, because I didn't touch it. R here. Parallel means divide by 2, just single R. And what can I do now? Only one resistor is left, 2R. And now I can use 1, 2, 3, 4, 5 different circuits to answer any questions. For example, this voltage 10 should split evenly between these two, 5 volts and 5 volts. So that's supposed to be 5 volts. So that's supposed to be 5 volts, which means I should split it here evenly, 2.5 volts, 2.5 volts, which means that's supposed to be 2.5 volts. And if we had bulbs, we could speak about brightness, because power is brightness, like knowledge is power. Any questions? All right, in that case, we stop here, and tomorrow I will spend maybe 10-15 minutes on your questions if you have, but tomorrow I will also start a new topic which will not be a part of the exam. bring downstairs.
While,
Yeah, I am done with this stuff.
it was
And
better
Grace
one.
might use it maybe next week,
know.
so we can keep it downstairs.
I'll see you yeah, I'm gonna look up the swirl. But yeah.
By the way, the system today, yesterday didn't work for me for a couple of times. Today it didn't work for me a couple of times. I think it's breaking down. System. Я не мог. Этот порт не работал вообще.
Понятно, ну ладно, сейчас попробую.
У меня все закрыто. Вот здесь сейчас
У меня сейчас воркшоп.
каждый день?
Нет, один раз и все. Если она сейчас работает, это будет неплохо.
Утром у меня сломался мой основной компьютер, мне пришлось заменять его.
В принципе,
Потом с этой системы забрать.
может день просто такой.
Yes. Yes.
I don't know if I should go to the office hours. There's
Well, first of all, they don't even have it, so, but still. Yes. All about capacitors.
yes. You just saw and then the question said, find the charge of each capacitor. Didn't go through with it, you just left it at that, so I tried solving it by myself, and got a little bit stuck.
So we did this, and then we did this, so we know all capacitance, all.
So I did that. Like to find the total charge.
Yes.
So I did that, and I was so I was just unsure how to solve it because higher than 6 volts.
First of all,
The first one and the second one were equal before.
this plus this equals still, which is equal to this.
Yes.
Yes, that is correct. Now, Q1 is equal to Q2.
No.
Yes,
Is it? Is
Q1 is equal to Q2.
oh.
Yes. And the charge you have found. What is this? This is for the top part.
Yeah, this is how I just draw visually to understand the
Alright.
series.
Root, and you should walk with me.
Okay.
You will be in the way. Small room.
Sure.
Go ahead, go ahead.
No, it's
It's either or, I'm locking the door.
oh.